writing a piecewise function. In a previous video, we took a piecewise function equation and learned how to graph it. Now we're going to work in the reverse order, where we're going to be given a graph and we want to write the piecewise function equation. Now we are going to limit the pieces and components of our functions that we see on the graph to just linear and constant functions. And the reason being is because higher degree polynomials or other functions that show curvature are much too time consuming to actually figure out what the equation is, or we may not actually know what type of function is represented with that curvature unless we're explicitly chosen, or we might not even have the toolkit at this point in our math careers to know how to actually write that equation. So we are going to stick with linear and constant pieces, and having said all that, we'll begin. Below the graph, I'm going to write our piecewise. We're going to call it function f, and our input variable will use x. And I can see that there's 3 pieces to this piecewise, so I'll leave enough room for 3 rules in my brace. We'll work one by one, left to right. So let's start with piece 1 all the way to the left. We can see that that's a linear function. To write a linear function, we need 2 pieces of information. We need its slope, or its rate of change, and we need a point that it passes through. And if we have those 2 pieces of information, we'll be able to get the function rule for that first component of the piecewise. So let's first determine slope. Now, to determine slope, we have to do a change in its output, or change in y, divided by its change in its input, or change in x. So that triangle representing delta, or change in. In order to express change, we need 2 points of reference. So you're going to have to identify 2 coordinates for this first piece. So let's say we use that open circle, -2, -2. That's a point it passes through. And then we'll also identify an additional point, which looks like -3, -4. So try to choose points that are on intersections between these grid lines. So it's on a lattice point, easy identification. Now, change in y, we can say -4 minus a -2 over the change in the x coordinates, -3 minus a -2. When we simplify this, we'll get -2 over -1, which is 2. So we have the slope of our first linear equation. Now, we need a point that it passes through. Well, the good news is we already identified 2 points in order to calculate the slope. So it is up to you which of those 2 points you want to use as the point this linear function passes through. So let's use -2, -2. And once we have a point and a slope that we want to use, we're going to use this general form called point slope form, which will get us the equation of this line. So how does this work? Well, y sub 1 and x sub 1 are the locations where you're going to input the point that the line passes through. Then this m variable, much like the traditional slope-intercept form that you are likely familiar with, represents our slope. Now the y variable and the x variable without the subscripts are going to stay as variables. So having said all that, let's write the equation of this line. So we're going to do y minus the y coordinate of the point it passes through, and we're going to use -2, -2. So it's negative of a -2, which ultimately becomes +2. The slope is 2. And x minus a -2, which is +2. So again, the point I'm using is -2, -2 of the point it passes through. So here we have the equation of this line. But we just want to make sure it's formatted in a way that I could carry it over to this piecewise. The piecewise is defined as f of x equals. We know f of x is function notation that is synonymous with y. So I just want to make sure that this linear function that I just wrote is solved for y, so I can take that expression that's defined solely in terms of x and carry it over into the piecewise brace. So we're just going to solve for y here. We're going to distribute this 2 to get 2x plus 4, but then I have to move this +2 to the other side through subtraction and ultimately get 2x plus 2. So this final form is that traditional slope-intercept form that you are used to, where we have mx plus b. Now you may be wondering why we don't use that instead of this point slope form, and the reason being is because this slope intercept form, yes, we need a slope for it, but this plus b is a very specific point that the line passes through. It is the y-intercept, which we could find, but it may require additional steps and may not always be easily identifiable if that was your hope. What you may have to do if you want to use that form, or what you'd likely have to do, is use a point that it passes through, plug it into x and y along with the slope, and then solve for b, and then back substitute in to get your slope intercept form. So to avoid all that, we just start with this point slope form, where we can use any point that the line passes through, and we don't even have to worry about ultimately finding a y-intercept, because that will take care of itself when we solve for y. So now we have that equation for the first piece. Let's carry that over, 2x plus 2. So now let's look at the second piece of our piecewise. The second part of our piecewise is a constant function. Now, a constant function is technically a linear function. It's just that the slope is 0. There is no rate of change. As the inputs change or increase, the outputs do not fluctuate. They stay at 3. So it has a slope of 0. So if we want to treat it like a linear function, which we can just to show you that they are the same, we have slope of 0. And again, we can calculate that by picking any 2 points. We have negative 2, 3. And we also have 0, 3. And if you calculate the change in y over change in x, we'll see that it equals 0. We do 3 minus 3 over 0 plus 2, so minus a negative 2, and we get 0 over 2, which is 0. Okay, so the slope is 0. And if we use a point it passes through, say 0, 3, we could say y minus the y-coordinate of the point it passes through equals the slope, x minus the x-coordinate. And we see those zeros, everything's going away on the right, and we just have y minus 3 equals 0, and therefore y equals 3. So in the event that you misidentify the constant shortcut, you can still treat it as a linear function and go through that process and get the second piece. Now, what is the shortcut for a constant function? We should be aware that a constant function equation is just a numeric value, and that numeric value is the point that the constant function is passing through on the y-axis. Now, why is it called a constant function? Because for any input value along the x-axis, the output remains constant. It's always the same. So there's our second rule, an easy one. And then last one, we have another linear function. We need 2 points, so let's identify 2 points on this piece. We'll say we have 3, negative 3 here, and another point, we'll say 5, negative 5. So we have to calculate slope, so we're going to do change in y over change in x. We're going to get, looks like negative 2 over 2, which is negative 1. Point it passes through, I could use either of those 2 points. So let's say we use 3, negative 3. So we're going to do y minus the y-coordinate passes through, so minus the negative 3 becomes plus 3 equals the slope, x minus the x-coordinate. We want to solve this for y because our piecewise is solved for y. So we're going to distribute this negative 1, and then at the end we're going to move over that plus 3. So we're going to get y equals, we'll have negative x plus 3, and then minus 3, we'll just have negative x. Now there's one last thing we must add on to our our piecewise function, and that is the inequalities at the end, which dictate along what intervals are these rules applied. So if you'd like, working off of that video that tells us how to take a function and graph it, remember we input these boundaries. We can identify those boundaries if it helps you to split up the sections and identify the inequalities for each rule. So we can see that this first rule all the way to the left is going to be applied whenever x is less than negative 2. So you can see that this first part of the graph is only in a section to the left of negative 2. Now, negative 2 is not included in that interval, and that is denoted by that open circle. So we're going to say this first rule applies when x is less than -2. Now the second rule, the constant function rule, is going to be applied when x is between -2 and 3. So that middle section of the graph, -2 is included in that interval. So we want to say -2 is going to be less than or equal to x, which is going to be less than 3. 3 is not included because of the open circle. And then for the last section, this last piece is applied whenever x is greater than or equal to 3. It could be equal to 3 because it's closed circle, indicating that it is included in the interval. And we can see it's everything to the right of 3 will be included. And these arrows indicate that they do go on forever. So for that first section, I don't want to say that it goes from -2 to -4. We know that arrow indicates it keeps going towards -infinity. And using that same thought process, we know the far right portion is extending beyond what looks like 6 towards positive. Okay, so we're going to say that this is when x is greater than or equal to 3. So we have all three components to our piecewise that we're looking for. We called it function name. We designated an input variable x, traditional. We have the three function rules for each piece. And then we have the inequalities that dictate when the function rule will be applied for the specific domain values. So that's how you write a piecewise function. And again, we are going to limit ourselves to linear and constant. So make sure you know what you need to write a linear function. And having said all that, the way we'll end this video is looking at an application. So a bug wakes up and walks for 3 hours at 50 inches per hour. It gets tired and then walks at 35 inches per hour for 2 hours. It gets even more tired and walks for 1 hour at 15 inches per hour. Graph and write a piecewise function for distance versus time. Okay, so we want to figure out what the input and output variables represent. And one of the things I want to highlight is this part of the first sentence here, 50 inches per hour. So we can write that in the following way, 50 inches per 1 hour. And when I see that, that to me represents a rate of change. It's telling us for every 1 hour we move, this bug will travel an additional 50 inches. And knowing that a rate of change equals slope, and we know slope is change in y over change in x, we can see that our x variables are going to represent time and our y variables are going to represent distance. So let's label our axis. We'll say this is time, specifically in hours, and then our y-axis is going to be distance in inches. Now, for the time axis, it looks like we're walking 3, then 2, then 1. So we're traveling for a total of 6 hours. So we can just count this off by ones. And then if we're going to label our distance, we're moving 50 inches per hour. So that indicates for those 3 hours, those first 3 hours, remember that 50 inches per hour is a rate of change. So it's not telling you how far you've gone over the total 3 hours. It's just saying per hour you've gone 50 inches. So for 3 hours times those 50 inches per hour, we've now traveled 150 inches in the first 3 hours. For the next one, it gets tired, walks 35 inches per 2 hours. So 2 hours times 35 inches per hour, another 70 inches has been traveled. And then 1 hour at 15. So if we add up these inches that are traveled in each segment, we see that we will have gone 235 inches total. So 235 inches total in distance have been accumulated. So we just want to make sure that when we're writing the labels for each line or each tick mark on our vertical axis, that we're going to be able to cover that total distance. So there's 10 tick marks, so I'm going to count by 25s. All right, so now let's plot the graph, because often after we draw the graph, it's easier to write the piecewise afterwards. Now, here's the other thing we're going to assume, that this bug is traveling at a constant rate of change. By assuming a constant rate of change or a constant slope over the time period for each segment, we know we'll be able to draw linear functions. If we assume that the rates of change are fluctuating and on average they're 50 inches per hour, then we're going to have a situation where we're not going to be able to write the piecewise function given what we know at this point in our algebra class. So assume that all the pieces are linear because of the constant slopes. Assume that they're traveling at 50 inches per hour for those 3 hours at that constant rate, and so on and so forth for the other rates of change. So if we're going to start at 0 time, 0 inches have been accumulated. So we're starting at 0, 0, and for 3 hours, we're going 50 inches per hour, which we already know over those 3 hours we will have gone 150 inches. So we have 3 150 as a point, and I'm going to draw a line that connects those 2 points. Then, for the next 2 hours, we're going an additional 70 inches. So it's not that we're going to start back at 0, 0 and draw another one from 0 to 2. We're going to tack on that new time. So we're going, starting at 3 hours, we're going over to 5 hours. We're going to go another 70. So we're going to go up to 220. So 5, 220 is our new point. So we're just going to ballpark this. So that will show that we've gone. So why don't I label these points as we go as well. So we have 3, 150. We have 0, 0 to start. And then we also have 5, 220. And then the last point is another hour has passed. We've gone another 15 inches. So we're at 6 hours total, 235 inches total. And we'll bar park that. And that's why it's good to label if you have to ballpark a location of a coordinate. So someone observing your work will know what you're referencing. Okay, so we have all these points labeled. You can see that there's 3 pieces, so now we have to write the piecewise. So we have all linear pieces, and we already discussed how to write linear equations. So let's look at the first piece. The good news is we already have the slopes for all these. So 50 inches per hour, rate of change, that's slope. 35 inches per hour, that's a rate of change, that's slope. And 15 inches per hour, rate of change, slope. So for the first one, we already have the slope, it's 50. And if you wanted to calculate that out by hand, by doing change in y over change in x, you can verify that. The point it passes through, you can choose either 3, 150 or 0, 0. I'm going to choose 0, 0. So y minus the y coordinate equals the slope, x minus the x coordinate, solve for y, and we're going to get 50x. So that's the first part of our piecewise. And why don't I mark off some room to write that piecewise function. So let's say we'll write the piecewise here. We have 3 pieces. The first one is 50x. So for the second piece, also linear. Slope we know is given in the problem, 35 inches per hour, so we know the slope is 35. Again, if you didn't recognize that, you should still be able to calculate that between the 2 points. So if you do 220 minus 150 over 5 minus 3, you'll get 35. Point it passes through, you can use 3, 150 or 5, 220, it doesn't matter. So y minus the y coordinate equals the slope, x minus the x coordinate. We're going to solve for y. So 35x plus 45. And for the last piece, we have slope is 15. Point it passes through, I'll use 5, 220. So y minus 220 equals 15, x minus 5. So we're going to get y minus 220 equals 15x minus 75. And y equals 15x. And we're going to do plus 145. Now the only thing left to do is to mark off these domain restrictions. So for the first one, the bug wakes up and walks for 3 hours. So for hours 1, 2, and up to 3, so we're going to say from 0, we could include 0 or not. We'll say that the thing starts after 0 or kicks in right after 0. So we'll say time and then less than or equal to 3, or let's include 3 in the next. Correct. So then from 3 to 5, and then from 5 to 6. So first 3 hours, next 2 hours, last 1 hour. We can see that 6 hours total have been covered from those inequalities, and we have the rules associated with them. So there's an application problem in which we had to graph. We can identify slopes from the context of the problem, writing the equation from the graph, 3 linear pieces. And again, to summarize, you need 2 things to write a linear function: its slope and a point it passes through, and get used to using that point slope form. It is very useful when those are the 2 pieces of information we have and it's not easy to identify a y-intercept. So that would be the conclusion of the video on how to write piecewise functions with linear and constant components.